Hi guys, today we're going to go through extracting metals. It's part of the chemical changes topic. In previous lessons we've looked at the reactivity series, displacement reactions, half equations, reduction, oxidation. So that's some really good background knowledge that we need to have to get through this lesson today. Feel free to go back to the previous sessions if you need to. Right, so we've seen this before. We've got our reactivity series of metals, most reactive to least reactive. Now, most of these metals need to be purified before we can make use of them. There are, however, metals here that are so unreactive that when they are dug up or mined up, they are found in their native state. Those metals are silver, gold, and platinum. They're so unreactive that they don't even react with oxygen in the air, which explains why they're used for things like jewellery. The rest of the metals, however, are not found in their native form, and so chemical processes need to be used to purify them. We'll be going through one of those processes today, and the other process comes up in our next topic. Right, so silver, gold and platinum, the least reactive metals on our reactivity series. They remain pure while they are underground. So when they are found or dug up, that is the main kind of form of extraction for those metals. They could be alloyed, which is like mixing them with other metals to change their properties slightly, but generally they are found in their pure native form because they are so unreactive. The rest of the metals, however, are often reacted with usually oxygen, and so the oxygen needs to be removed to purify them. Now, I'm sure you've seen this before. You've got a picture here of a mine, and many metals are found in the ground as compounds in ores. Okay, now you need to know this definition of a metal ore, which is a rock that contains enough metal for it to be economical to extract. So it's got to be worth that company's money to extract it, because this is quite an expensive process. There's a lot of heating involved, high energy costs, etc. So it's got to be worth the time and effort. Now, once the ore is removed from the ground, the bits of rock are crushed or removed from it, and the compound has to be chemically separated. So there are two methods: reduction with carbon and electrolysis. Electrolysis comes up in the next chapter, so we won't be going into too much detail for this topic, but we do need to know about reduction with carbon, which is what we'll be covering today. Now, if we remember when we first looked at the reactivity series, we've said that there were two elements on here that were not metals, but very important as a reference point. So one of those elements is carbon. Now, carbon is more reactive than zinc, iron, tin, lead and copper. So what we can say is that carbon is able to displace those metals out of their compounds, and as a result, the products would be a pure metal and carbon dioxide. Now, usually these metal compounds in ores are metal oxides, and so essentially the metal oxide is heated with carbon in a blast furnace at really, really high temperatures. And the products would be carbon dioxide and the pure metal, which can simply be poured out. So just remember, guys, there's two meanings for reduction. It's the gain of electrons, which we'll be looking at in a minute, and the removal of oxygen. So we can remove oxygen from metal oxides by heating them in a blast furnace with carbon. Okay, so this is our first chemical process that you need to know about. Okay, excellent. So if we say that our general rule is metal oxide plus carbon makes carbon dioxide and a pure metal, then what I'd like you to do is complete the equations by balancing them, and also writing any missing elements or compounds, and also writing the correct state symbol. So if you just pause the video, maybe give yourself, let's say, 5 minutes, and then check your answers. So just pause the video now and try these. Okay, right, let's check your answers. So you'll notice that all of these equations show the reduction with carbon. So we've got, in every case, for the metal oxides, the oxygen gets removed. That oxygen binds to the carbon. We always make carbon dioxide gas, and the pure metal is formed. So that is how we can extract metals from metal oxides, using carbon, but only when carbon is more reactive than that metal. Okay, right, we're just going to take this up to the next level by actually looking into the reduction of the metal in each of these reactions. So if I do the first one as an example, you can try the others on your own. So you've got copper oxide plus carbon makes carbon dioxide plus copper. So really, really important industrial process. There is a real high demand for metals like copper. They're used in water pipes, electrical wires. So very, very important industrial process. But copper itself is not a native metal. It's not pure. It has to be purified by removing the oxygen from the compound. So if we start by, I'll give you the word equation, but the first thing I want you to do once you have the word equation is write the balance symbol equation, which we've done before. Then remember, guys, from part 1, when we were writing out the formula of ionic compounds, the charges need to add up to 0. So if we look at copper oxide, well, we've got, for every 1 copper, there's 1 oxygen ion. So remember, oxide ions always have a charge of -2. Therefore, if I've only got 1 copper, that would have a 2+ charge. So our copper has gone from having a 2+ charge to no charge. So that's clearly reduction. We've got carbon displacing the copper out of the copper oxide because it's more reactive. So the oxygen's been removed, but also our copper has been reduced because it's gained, in this case, 2 electrons. So that would be the half equation for 1 of the copper ions in this reaction. Right, I want you to use the same layout for the next 3 examples. So try this one yourself. Lead oxide plus carbon makes carbon dioxide plus lead. Write the balanced symbol equation, and then please write the half equation to show the reduction of lead. So pause the video and try that. Okay, let's check your answers. So very similar to the copper example, we see that oxygen's been removed from lead oxide, and that lead has been reduced each lead ion has a charge of 2+, therefore gained 2 electrons to form lead. So that would be the half equation for one lead ion. Well done if you've got that right. Let's try the next one. So we've got tin oxide plus carbon makes carbon dioxide plus tin. Remember guys, the number in brackets indicates the charge. So in this case, we've got 4. So our tin ion has a charge of a 4+. So remember, you need to make sure the charges add up to 0. So write the formula or write the balance symbol equation, then write the half equation to show the reduction of tin. Pause the video and try that now. Okay, so let's check your equations. So if the tin has a charge of +4, that means our oxide has to have a charge of -4. If each oxide ion has a charge of -2, I need 2 oxide ions for every 1 tin ion. So that's why my formula is SnO2. We can see oxygen's been removed. If the charge of our tin is +4, it has to gain 4 electrons to lose that charge. Excellent. Okay, and the last one. Oh, I just jumped ahead there. Right, try this one please. Iron oxide plus carbon make carbon dioxide plus iron. So I want the symbol equation and the half equation to show reduction of ion. So pause the video and try that. Okay, let's go through this. So first thing that I've noticed is my ions have a charge of 3+. So that would mean I would need 2 iron ions and 3 oxide ions to make those charges add up to 0. And if I balance the equation, this is what you should get. You've got the removal of oxygen and the gain of electrons. So we'll just show the half equation for each ion. So each ion gains 3 electrons and we form pure iron. Again, really, really important industrial reaction, lots of uses for iron. Okay, excellent. So that's our first chemical process. Like I said, in the next chapter, electrolysis is used for those more reactive metals more reactive than carbon, because carbon wouldn't be able to displace them even in a blast furnace. So we have to use an alternative method. But we have covered reduction with carbon and native metals, and electrolysis will come up in the next topic.